The confusion matrix is often used to assess bias in prediction and decision processes. There's a lot of concern these days about algorithmic bias, which can happen when predictions and decisions are made by machine learning algorithms trained on data. Does the confusion matrix help us measure algorithmic bias? Well, the answer is yes and no. Maybe. Sometimes. It depends. If that sounds confusing, well, it is confusing. The confusion matrix dashboard shows that as a tool for measuring algorithmic bias, the confusion matrix behaves in a lot more subtle and complex ways than it might seem. Only recently it was proven mathematically that the various terms in a confusion matrix cannot possibly give a single, unified measure for algorithmic bias. If you've got two subpopulations with different base rates and distributions of positive and negative predictions and outcomes, there are inherent contradictions between aligning false positive rates, false negative rates, precision, and the other conditional use measures. I think the best way to disentangle confusion about the confusion matrix is with an example. So let's work through an entirely made up but realistic example. The example is called apple snacks. Imagine that you're packing snack boxes for a school picnic. Some of the kids like apples, some prefer something else like popcorn, a cracker, or a cookie. You have two kinds of snack box, one with an apple and one with something else. You must decide in advance which kind of box to give each kid, which you will then label with their name and hand out to them. When each kid opens their snack box, they will either be happy with their snack and say, "Yay!" or else they will be disappointed and say, "Aw." To help you decide, you predict which kind of snack each kid likes based on some rules of thumb. Older kids tend to like apples, while younger kids do not. Taller kids like apples, while shorter kids don't. Kids in Mr. Applebaum's class tend to prefer apples, while kids in Ms. Popcorn's class want something else. There is no hard and fast rule, just an educated guess. Here, we're dealing only with binary decisions. Multi-class decisions produce confusion matrices with more rows and columns. That would be if we broke out other kinds of snack between popcorn, cookies, potato chips, whatever. But here we only have a binary decision, two choices, apple snack or other snack. For each kid, you give them a point score indicating the likelihood they will want an apple. A score of 10 means you are quite sure they'll want an apple, for example, a 10-year-old girl in Mr. Applebaum's class. A score of 1 means you're confident they will not want an apple, like a 6-year-old boy in Ms. Popcorn's class. For each kid, after calculating their prediction score, you make a decision. You might set the decision at the midpoint score of 5, or you might set the apple snack threshold higher or lower. For example, if it's important that the kids eat fruit, you'll set the threshold lower so that you'll catch more kids who prefer apples. Or if you want to err on the side of having fewer apple slices discarded in the trash, then you'll set the threshold higher, so fewer apple snacks are handed out. In other words, your decision depends on the trade-offs for different kinds of errors. At the picnic, you record kids' reactions. You write down what prediction score you gave them, whether you gave them an apple or not based on the decision threshold, and what their reaction is. The reaction is the payoff for your decision. After the picnic, we build our confusion matrix. We put the condition negative, the kids who do not want an apple, on the top row. We put the condition positive, the kids who actually wanted an apple, on the second row. And in the columns, we put our predictions. Negative predictions on the left, positive predictions on the right. The confusion matrix counts the numbers and ratios for each quadrant of the table. So that's the problem setup. Now let's start to look at how the confusion matrix behaves. The behavior of a confusion matrix depends on the distribution of positive and negative outcomes along the horizontal prediction score axis. How many kids who really wanted an apple did we manage to give a high score to, while keeping kids who didn't want an apple on the left side of the graph, where we could separate them by a good choice of decision threshold? We need some data. And in order to experiment with the behavior of the confusion matrix, especially when we're concerned about bias, then we need some data whose behavior we can control. So let's make up some data. We'll build a data synthesizer. The Python code for the Apple Snacks data synthesizer is in the GitHub repository for this project. I'll explain how it works. We're going to generate some pretend kids, as many samples as we want. For each pretend kid, we'll imagine that they have 4 attributes that contribute to a probability that they'll want an apple snack versus other snack. Each kid ranges in age between 6 and 10. Each kid has a height between 40 and 60 inches. Each kid has one of 3 teachers, Mr. Applebaum, Miss Fruitdale, or Ms. Popcorn. And each kid has a pet. The pet can be a turtle, a fish, cat, or dog. We'll generate these attributes at random for each kid independently, but we will allow these attributes to take different distributions. We'll call these generator distributions. Sometimes we'll have our synthesizer generate kids' ages evenly across the range of ages. Other times we'll allow the ages to skew younger or older. Sometimes we'll say that all kids have each kind of pet with equal probability. Other times we might imagine that more boys have turtles and fish, while more girls have cats and dogs. These are the knobs we'll use to control our distributions. From different generator distributions, we'll explore how the confusion matrix behaves. Now, how do we generate the pretend distributions for apple snack or other snack? By sampling. Here's how we generate a pretend kid. We pick an age, height, teacher, and pet by drawing from generator distributions for these attributes. Then for each attribute, we define an amount that the attribute contributes to a preference for apple snack versus other snack. Let's say that for age and height, the preference for apple increases linearly with these attribute values. And for the categorical values, let's say that Mr. Applebaum counts a coefficient of 2 toward apple, Ms. Fruitdale counts 1, and Ms. Popcorn counts 0. For pet, let's give turtle a 0, fish 1, cat 2, and dog 3. These are arbitrary made-up coefficients. They'll stay fixed across all experimental conditions. Because some of these numbers fall in a larger range and some smaller, we'll do some normalizing. Then we sum them up. This now gives a prediction score for our pretend kid. Let's treat the prediction score as a probability that the kid wants an apple snack. I mentioned that we're normalizing to make the bins represent a probability from 0 to 1. Given the prediction score that is now a probability, we'll sample that to arrive at a final outcome. Does the kid really prefer an apple snack or other snack? This is the outcome variable, red for apple snack, green for other snack. We do this for hundreds or thousands of pretend kids, and voila, we have our synthesized samples. The distribution of kids' preferences will track the prediction scores. Because we're sampling using a random number generator, there will be sampling noise. Let's generate 100,000 pretend kids, just to smooth out the statistics. Now that we have our synthesizer, we can look at the confusion matrix for various experimental conditions. Condition 1, uniform. For starters, we'll use uniform distributions as our baseline. The generator distributions are all uniform. It's equally likely for all kids to be any age from 6 to 10, to be any height from 40 to 60 inches, have any teacher, and have any pet. What does the distribution of prediction scores look like? Well, it's kind of a bell shape. That's due to the central limit theorem, because we're adding together scores drawn from 4 independent generator distributions. But when we draw positive and negative outcomes from the scores at each bin, then we draw more green negative outcomes of not wanting an apple on the left side and more red positive outcomes on the right side where kids' preferences for apple snacks are higher. So the breakdown of negative and positive outcomes takes the form of these 2 overlapping bell curves. How well are they separated? The ROC area under curve is 0.7, which is considered not bad, even though we can still see there's considerable overlap. With the decision threshold set right in the middle, the true positive and true negative rates are 0.64, and the false positive and false negative rates are both 0.36. The positive prediction ratio curve, here, the tan curve, is a nice straight line, which is simply an indication that the sampling has produced distributions of negative and positive outcomes that faithfully reflect kids' preferences indicated by prediction score. As with any data set, we can adjust the decision threshold to trade off true positives, true negatives, false positives, false negatives, precision, and other conditional use measures in the confusion matrix. Is there any bias going on? No, there's only one population of kids, all drawn from the same generator distributions. There's no bias. Condition 2, skewed same. Next, we'll use some skewed generator distributions. We'll tilt the age and height distributions toward the high side so that more older and taller pretend kids are generated than younger and shorter. And we'll skew the categorical attributes toward Mr. Applebaum as teacher and toward cat and dog as pet. The result is the kids' preferences will skew toward preferring an apple snack with higher prediction scores. In condition 2, boys and girls have identical generator distributions and their prediction scores are congruent. Condition 3, skewed opposite. For condition 3, we'll make things interesting and use different generator distributions for girls and boys. For girls, we'll use the same generator distributions we just used for condition 2, so girls in this example will tend to be older, taller, have Mr. Applebaum as teacher, and have cats or dogs as pets. Therefore, they trend toward preferring an apple snack. Then for boys, we'll skew in the opposite direction. We'll suppose that, for whatever reason, at this school the boys are younger and shorter, they more likely end up in Ms. Popcorn's class, and they tend to have turtles and fish as pets. As a consequence, boys tend toward preferring other snack. Is it unfair that in this particular made-up school, girls tend to like cats and dogs while boys like turtles and fish? That would be hard to argue. We're just making up this data. Some real schools might have kids with these attribute distributions. Here's what these distributions look like in the confusion matrix dashboard. Now, girls' distributions are skewed to higher prediction scores. We see this most clearly in the shape of the stacked histogram. Boys are reversed, with their peak scores off to the left side. The positive and negative outcome distributions that were generated by sampling created a sizable preference for apples for girls, which results in a 58% base rate for girls preferring an apple snack. Boys are the reverse. Now, what do the respective confusion matrices say about false positive and false negatives? With the decision threshold set right in the middle, girls have a false positive rate of 0.54. That reflects the fact that 54% of the green or negative preference distribution falls on the right side of the threshold. But for the boys, the green curve is set much farther to the left. The tail that extends above the threshold is much smaller, giving boys a false positive rate of only 0.22. The converse is true for false negative rate. For boys, it's 0.54, but for girls, the false negative rate is 0.21. Does this mean that there's prediction bias? And if there is it biased for or against girls or boys? We can look at the confusion matrix from the point of view of true positives and true negatives. The true positive rate for predicting girls to prefer an apple snack is 0.79, while for boys, it's only 0.46. So if you like apples, you might say that girls are advantaged because the girls who want apples get them 79% of the time, while the boys who like apples get them only 46% of the time. But if you don't care for apples, you could say that boys are advantaged because boys who don't want apples get their preference with a true negative rate of 78%, while girls who don't want apples get their preference only 46% of the time. Some people think there's a bias when the false positive and false negative rates are different between different populations. The confusion matrix dashboard shows that we can actually bring them into alignment. If we move the decision threshold for girls higher, say to bin 11, and move the decision threshold for boys lower, down to 8, then now the ratios are almost identical. In so doing, we've moved the decisions for girls and boys to the same trade-off point on the ROC curve. However, by adjusting the thresholds, we bring the precision and the other conditional use measures more out of alignment. Now, when a prediction is made that a girl wants an apple snack, it is correct 69% of the time. But when it's predicted that a boy wants an apple snack, that's correct only 54% of the time. And it seems very unfair to set different decision thresholds for girls and boys. In doing this, the girls and boys who have no strong preference for an apple versus other snack, the ones in the middle here, will get treated differently. The boys will find themselves on the right side of their threshold and receive an apple, while the girls are subject to a higher threshold and will receive the other snack. Here's another way to look at the different distributions of girls' and boys' preferences. The tan curve shows the fraction of apple preference at each prediction score. That's called the positive prediction ratio curve, or PPR curve. Amazingly, even though the locations and sizes of the green and red preference distributions for girls and boys are very different, their PPR curves are the same. This is called calibration accuracy. We can see that by toggling this little checkbox. That causes the PPR curves from these two panels to show up on the opposite panel, so we can compare them directly. This score here, the PPR score, is a weighted measure of the area between the curves. I discussed that in a different video. The thing to note is that number is small in this case, only 0.01. That shows that the positive prediction ratio curves are well aligned, which means that the prediction scores are accurate with respect to the preferences for apple snack for both boys and girls. That's not surprising since we generated the data to be that way. But what we learned from this example is that data can be generated totally fairly, but have different outcome distributions for two subpopulations. If the two populations are treated equally with respect to decision score, then the entries in the confusion matrix can be very different. That tells me that true positive, true negative, and false negative rates in the confusion matrix are not good indicators of prediction bias. That's because these measures are subject to different prediction distributions and different base rates that might be characteristic of different subpopulations. Condition 4, skew opposite bias girls. So what does prediction bias actually look like? We can generate data that clearly does have bias. One way is to take the girls' scores from condition 3, where girls are skewed to prefer apples, and just reduce the prediction scores by a constant amount. Just slide the girls' green and red preference distributions to the left. Now, confusion matrix ratios are actually closer for girls and boys than they were before. And you only need to displace a threshold by one bin to bring them into alignment. But the result is that significantly fewer girls are receiving an apple snack than boys who have identical preferences. For any given prediction score bin, the fraction of girls who want an apple is considerably higher than the fraction of boys who want an apple, and that makes a difference in satisfied kids no matter where the decision threshold is set. This is indicated by the positive prediction ratio curves. We see that the girls' PPR curve is uniformly higher than boys. There is a consistent gap between the curves, and the PPR score is 1, which is an indicator of calibration bias. Condition 5. Uniform randomized girls. Another way to introduce prediction bias is to degrade prediction quality for one of the subpopulations. In condition 5, we first generate prediction scores uniformly and identically for girls and boys, as in condition 1. But then we randomly select 1/3 of the girls and reassign them a random prediction score. So for example, 1/3 of the girls who strongly preferred an apple snack will get reassigned to a different prediction score bin, and some of that time it will result in their falling on the other side of the decision threshold and not getting an apple. When we look at the girls and boys subpopulations, we see that the girls' distributions are squashed flatter to be closer to a uniform distribution of prediction scores. As a result, the positive prediction ratio curve for girls is wavy, which means that a bunch of girls are not getting their preferred snack. The PPR score is 0.75, a clear indication of mismatch between the curves. And the girls' ROC curve is significantly degraded to an area under curve of only 0.62. This is a situation where the two subpopulations are clearly out of calibration in the prediction scores kids are given with respect to their statistical preference for a snack. Because it's a made-up example, the synthetic Apple Snacks data lets us explore the behavior of the confusion matrix without confounding difficult societal issues where bias really matters. Different subpopulations can have different outcome distributions not because of algorithmic bias, but because of different underlying characteristics. And these different outcome distributions lead to disparities in terms of their respective confusion matrices. If two populations have different base rates of positive and negative outcomes, then the confusion matrices cannot be brought into alignment. That's just the math. If you have a situation where a decision threshold is applied to a continuous prediction score, load it into the confusion matrix dashboard and explore how the confusion matrix really behaves on your data.